Hi guys, welcome back to my channel. So today we're going to be looking at position vectors, but before we jump into our questions with position vectors, we're going to talk very briefly about conic sections. So conic sections are sections that are produced when a plane cuts through a cone. So there's four different types of conic sections. We have the ellipse, we have a circle, we have a hyperbola, and we have a parabola. So each of these different conic sections can be described using a Cartesian equation, or they can be described using a set of parametric points. So we're going to be using vectors expressed using the parametric equation. So we're going to have a function for x and a function for y. So let's jump in and I'll show you an example. So here we have a section that's described parametrically. So we have the x component here, which is our 3t take 4, and we have our y component here, which is 4t take 3. So we're going to start off nice and easy today. We're going to find the distance of the particle from the origin when t is equal to 2. So to do this, all we're going to write our formula, which is 3t take 4 I plus 4t take 3 j. And we're going to substitute in our value for t here. So 3 times 2 makes 6. 6 minus 4 is going to give me 2i. Same thing here. So 4 times 2 is 8. 8 take 3 is going to give me 5j. So this here is the vector equation. So if I was looking at this vector when t was equal to 2, then this is going to be the vector r here. So what we actually need to do, we need to find the distance of this vector. So we need to find the magnitude of this vector. So to do that, we're going to use our formula, the distance. So the magnitude is going to be given by the square root of x squared plus y squared. So here my x squared component is 2 and my y squared component is 5. So 2 squared is 4, 5 squared is 25. So overall, I'm going to get the magnitude of this vector at that particular point in time is going to be the square root of 29. So if we wanted to find the distance of the particle from the origin from any time t, well, we can just use this equation here. So this time what we're going to do is we're just going to substitute in our values for I and for j because we're looking for any time. So the magnitude at any time is going to be given by the square root of our x component squared, which is 3t take 4 squared, plus our y component squared, which is 4t take 3 squared. So that's it. So we can go ahead and we can expand that and we can simplify the terms. So let's jump in and have a go at that. So all I did there was just use that binomial expansion pattern. And then we can go ahead and we can simplify by collecting our like terms. So this is now going to give us the distance at any time. And again, that's just given by the magnitude formula, and we've substituted in those values for x and y. Okay, so this last question here now, question C, the closest distance of the particle from the origin. So the closest distance, we're thinking about minimizing the distance. So since this is a minimization problem, we're going to need to use calculus and differentiation in order to be able to solve. So since this is my formula for the distance of the origin at any time t, this is the formula that I'm going to be taking the derivative of. Just giving myself a bit more space here. So what we're going to do is we are going to go ahead and we are going to use the chain rule in order to find the derivative. So just as a reminder, when we're using the chain rule, what I'm looking to do is I'm going to find the derivative of the inside function and I'm going to multiply that by the derivative of the outside function. So let's simplify this a little bit. So if I rewrite this, I can rewrite this as y is equal to 25t squared minus 48t plus 25 to the power of a half. So that's the same thing as saying our square root. So I'm going to let the inside function 25t squared minus 48t plus 25 equal to u. So now I'm going to find the derivative with respect to t for my function for u. So this is going to give me 50t minus 48. So that's the derivative of my inside function. So now I can rewrite this y expression, and I can rewrite this as y is equal to u to the power of a half. So if I was going to find the derivative now of this function, so the derivative with respect to u is going to be equal to 1/2 u to the power of negative 1/2. Okay, so now I'm going to use my chain rule. So we have dy dt is going to be equal to du dt multiplied by dy dt. And this is a little bit algebraic here, because remember when we multiply, oh, sorry, I messed that up. That should be dy du. Because when we multiply these fractions together, these two terms are going to divide into each other, and that's going to be equal to 1. So this is how the chain rule actually works. So let's multiply these two numbers by each other, and again we can rewrite this as 1/2 square root of u. So we're going to write this as 50t take 48 all over 2 square root u. And remember, our value for u in the first place was 25t squared minus 48t plus 25. Okay, so that's our derivative. So again, since this is a minimization problem, what we're trying to do is we're going to let this value here equal to 0. So we're going to rearrange now to solve this equation for 0. So this is going to be equal to 50t take 48 is equal to 0. And therefore t is going to be equal to 48 over 50, which will simplify it to 24 over 25. So that's the time where the particle is closest to the origin. The last thing I'm going to do is I want to find the distance, so I'm going to substitute my value for t into my equation here. So we're going to have the square root of 24 over 25 squared minus 48 times 24 over 25 plus 25. So chucking that into my calculator, I get a value of 7 over 5. We can express this as a decimal. I'm happy to leave this as a fraction. So here we can see that the closest distance in meters of the particle to the origin is going to be 7 over 5 or 1.4, and this is going to be at t is equal to 24 over 25 seconds, I believe the units were. Alright guys, so that's just a very brief introduction into position vectors. So this is something that we've sort of seen a few times now. So we're just looking more about how we can use these vectors, or how we can apply these vectors to solve particular problems in particular contexts. Alright guys, I'll leave it there. I'll see you in the next one.